Problem 135, candy. There are n children standing in a line. Each child is assigned a rating value given in the integer array ratings. Something like this, right? So you are giving candies to these children subject to the following requirements. Each child must have at least one candy. That's fair. Children with a higher rating get more candies than their neighbors. Now that's a little bit ambiguous, but I'll get back to that in a second. First, let's say what we have to actually do. We have to return the minimum number of candies you need to have to distribute the candies to the children. So the minimum number of candies that could be used to satisfy these two requirements. So each child must have at least one candy. That's not ambiguous. Children with a higher rating get more candies than their neighbors. I think what they want to say is, if you have any pair, right? If you find any pair where there is a strictly unequal relationship of ratings, in that case, the number of candies must have exactly the same type of inequality relationship. So 3 and 7 here would be fine, but 8 and 7 wouldn't be fine. Or even the same number of candies would not be fine, right? And if another pair has the opposite relationship, strict inequality, then this this should be something like that. Again, we cannot have equality or something. So it must be, if there is a strict inequality in ratings, then between two neighbors, then there must be exactly the same type of strict inequality between their candies, right? But if two neighbors have the same rating, then they have no requirements. You can give them any number of candies you want, and this pair will not cause a trouble. Of course, it may have a requirement to comply with another neighbor, but in terms of this specific pair, has no requirement imposed on them. So that's what they probably mean. And with that in mind, let's try to proceed and see what we can do here. I would suggest that we, for developing some sort of intuition for this problem, come up with some sort of graph. So let's plot these ratings of these children on a graph and say, so let's say this is child 1, these are ratings. So children are on x-axis, right? And then on the y-axis, we have ratings. So rating of child 1, rating of child 2, rating of 3, child 4's rating. And then let's say we go really down here. And then same rating for child 6. We start climbing again, right? Small climb, but lots of children. And then suddenly I drop here and a small climb. You know what? I'm gonna change this to slightly even lower, all the way here. Yeah. Now let's put a line. A line through these points so that our intuition can really properly imagine what's going on. We can deal with lines probably slightly better than with these distinct points. So this is our line. Incredible. Right. Now, if you look at this, we will be focusing on these valleys, right? So these are valleys. Let's say these are equal to each other, right? So then these are valleys. And this is a valley as well. But most importantly, we'll be focusing on these peaks here, okay? And we'll be looking at the heights of these peaks from both sides, right? So in terms of the valleys, we can assign one. Maybe I should change color. So ones will be assigned to all of these valleys, right? And these are number of candies. So each child must have at least one candy, right? So because these are valleys, if we assign ones, one candy, that will be the best option for us. Now we have to start climbing the valleys. So as we climb these valleys, look at the height of the valleys. And I suggest to look at the height, not in the sense that this value in terms of the difference in rating, but the difference in terms of how many children in succession are part of this valley. So basically, how many points, how many of these little points high is the valley? Because that will matter, right? So if this one has one candy, this has to have two, and this three, and four candies on this side. Now, that was this valley here. But this is also a peak on the other side of the valley. Peak, sorry for that confusion. Now, if this child has one candy, this child must have at least two candies. But it must have four candies just to satisfy this peak here. So because this peak is higher on the left, so 4 and 2, so basically we'll choose and keep 4 for this peak, right? And we'll do the same for this peak as well. So this peak is 1, 2, 3, 4, 5 high from the left, and then just 2 high from this side. So 5 wins, and we're gonna keep number 5 here. And this pick will just have 2. So I think if you look at this, it's immediately obvious that this will be the optimum distribution of candy. We could easily prove that this is so, but let's not trouble you with that. Let's just try to implement this. And to implement, we just probably need, I mean, it's a little bit too early to implement. We just need to say how we are going to implement, right? This thing. How are we going to look at these valleys and peaks and everything? So I suggest that we do this. We traverse this array twice, once in this direction from left to right. And at this point, we'll take care of the peaks that go from left to right, basically. So these peaks that ascend from left to right. And then after this, after we're done, we traverse in the opposite direction. And this time we'll look at the opposite peaks. Yeah. So let's think how we're going to do this. So we're going to create a new array called candies. Probably a good idea to call it candies. And we're going to initialize this array to 1. So every value will be 1 in this array of candies, right? So now we're traversing from left to right. We're going to start looking at the second rating and say, is this rating greater than the previous one? If it is, then we are ascending into a valley. And then for this child, we need 1 more candy than the previous child. So this will be 2 candies. Now we're going to look at the next value and say, are we still ascending? If yes, then again, for this child, we need 1 more candy than the previous child. So 3 candies for this child. If we're still ascending, again, 1 more than the previous. And if now this relationship is broken, then we keep 1 here. This may not remain forever 1 because this could be a value from the opposite direction, but at least in terms of checking these values that go from left to right, this means the valley has been broken. So we do basically this. Let's actually do that and then talk about the opposite traversal. So we said we're going to create an array called candies. Let's set it to new array type number, and ratings length would be the length of our array. Fill it with 1. Now traversing. We said we're going to start from the second element. So candies, let I equals 1. That's the second element. Let's talk 0 index. So this is element with index 1, not 0. And then E must be less than candies length plus I. Now we said if we're going into a valley, which means if ratings I minus 1 is less than ratings I, that means we're going into a valley, and we should say candies I should be candies I minus 1 plus 1. I think so, yeah. So that's the traversal in one direction. Now let's do a traversal in the opposite direction. Rid of, I shouldn't have deleted the, that's fine. I shouldn't have deleted the values, but it's such a mess anyway that it may be. So some of these values could be basically 1, 2, 3, 4, something like this, yeah. Now we're traversing in this direction. So what we'll do is we'll check whether, first of all, we're going to start from the penultimate rating. And for each I, this I will be the current index of the current element. So we will check if rating of I is greater than rating of I plus 1, right? So if this is the case, then we're ascending in this direction because we're traveling that way from left to right. So if we have that relationship, then the left value is greater than the right value. So we're going up in the hill. And in that case, candies I must be, the maximum value. So here is a slight difference because this could already contain a peak from the previous traversal. It could already have some peak value. So we should keep it if it's bigger than what we're going to calculate now. So candies I will contain maximum of itself if in case it's a better peak, or it will be the new peak that we're going to be calculating. So this will be candies I plus 1 plus 1. So I plus 1 is the candies that previous child had. And it's plus 1, obviously, because previous from to the left. So candies of the previous child plus 1, right? Okay, if that makes sense, I think we can also do the second traversal. And the second traversal will be for let I equals penultimate, right? Candies length minus 2. And then we need all the rest of the elements. And we said if ratings I is bigger than ratings I plus 1, then we need candies I to equal to the maximum element of itself and candies I plus 1, the previous child's candies, plus 1. And at this point, candies contains the optimum distribution of candies. We just need to sum all of them up. So reduce, and we'll do sum plus next. We don't need to do start from 0 because we are assured that there will be at least one element. So this should work. Of course, if we return this value, then this should work. Hopefully this is all right. Let's see if I've made any typos. Let's see what's going to happen. Wrong answer. So potentially I messed something up. Candies length, if ratings I minus 1, that seems correct. Then candies I is candies I minus 1 plus 1. Now, sounds okay. This is wrong. So just check everything else. It looks fine. Okay. Good. We can now submit this. Let's see what happens. Okay. It passed. Nice.